Okay, so today I wanted to talk about PIR, private information retrieval. It might be a shorter lecture today. Let's see. Focus. Okay. So private information retrieval, abbreviated PIR, and I will not give citations. There is beautiful foundational work that all these people should be cited, but for citations, you will have to go to the class site and the syllabus. So there's links to some foundational work and to surveys. Here's the private information problem. It's the client has a index in between 1 and n, and the server has an array which is in the simplest setting, it's a bit array. So it's an array of n bits. And the PIR building block should have the property that the client learns the ith location in array X, and the server learns nothing from the interaction. Well, in particular, it doesn't learn. Well, the only thing there is for the server to learn, which is the client's input, the index at which the client retrieved a location in array X. So this is, of course, a case of secure computation, right? On these two inputs, we want the two parties to have these outputs, and it's privacy in this formulation is privacy preserving for both, for the client, because the server didn't learn the index at which the client retrieved, and for the server also. However, PIR might not care if C learns more. For example, more entries in X. The PIR's concerns are first privacy for C, i.e. I hidden from S, right? And the secondly, bandwidth must be sublinear in X. So here is the non-triviality of constraint. So if we don't care about the privacy for the server, so we allow the client to learn more about X than just the ith entry in X, then a server could just send his input to the client, and the client could retrieve this locally. But that would violate this, right? We want this delivery of the ith location to take less space, less bandwidth than the size of the array. And if we have a sublinear solution like this, then we can add actually the privacy from the server side So extension, this is called symmetric PIR. PIR, where symmetric means symmetry for privacy, and that would include that C learns only X of at ith place and nothing else. So once you specify this the symmetric PIR, what's the difference between OT, right? So this is 1 out of n OT. This guy has n messages. This guy has a bit, it has an index of the message, the one message out of n that he wants to retrieve, and he retrieves that one. The sender doesn't know which one. Okay, so the 1 and 3 define basically 1 out of n OT, right? But PIR, but symmetric PIR adds the two, the sublinear communication to OT, right? And if you think of this as a secure computation, we already have generic secure computation for any circuit. So here is what is the circuit that performs this lookup? Okay, it's not a complicated circuit, right? It's you specify this index, and the circuit for at every index basically ignores entries of X, and for the one index that matches, it outputs that one, right? So the circuit just defines a lookup table, right? It's but what is the bandwidth? Well, in the very least, I mean, every solution we have seen for MPC, the bandwidth of the computation is the number of gates, is proportional to the gates of the circuit, right? We said that for certain gates you can, in a GMW, XOR gate is for free. Yeah, you can modify so that the XOR gate is for free. Could you code it so that it's a very simple circuit? So maybe everything is an XOR there. But the one thing, I don't know, maybe it is or maybe it's not. Let's leave it as a question. But what cannot be, regardless of how you implement this circuitry, like even if you manage somehow to do very few non-XOR gates, which I somehow doubt is the case. I think that you have a non-linear number of non-XOR gates still. The input is linear. And all these solutions, they start by either GMW, secret sharing all the inputs. So already that is linear in N, or YAO, garble all the inputs, right? Like, and create keys for this and do OT. So this is the first time we're asking, okay, here is some computation. We want a sublinear communication in the size of input. And we don't get that in using the generic solutions. Now, okay, why? This is an incredibly, fundamental problem, right? And basically, it is a building block for many privacy-preserving database access, retrieval, and computation solutions. So this very basic lookup functionality has been upgraded, if you will, and put in place, where what is happening here is not just retrieval, but for example, computation, where this is a huge amount of data. This is some small query that should be somehow computed against the database, and the retrieve value is a short value, okay? But perhaps it's not just a retrieval, but a computation based on X. Could we perform such computations in a privacy-preserving way? So nothing learned about the nature of this query, and perhaps only the result of computation on the query as the information that is leaked about this database. But we want the whole thing to be to have sublinear computation in the size of the database. It's a very natural problem. The databases are huge. Any computation that we have seen so far violates this constraint, and essentially is not very practical when the databases are large. But this is a technology that basically breaks the barrier for secure computation to have it's not a general secure computation, right? It's just a retrieval, but it can be hooked, and it has many. Okay. There's two basic flavors of solutions that were given to the PIR problem. Two solution flavors. One is computational. Put the light here. Computational PIR, where you have on the right-hand side, you have one server, and computational privacy and what you get is computational privacy. So in some basic way, what the client does is that he encrypts the index, sends the encrypted index to the server, and the encryption has the property that the server can perform a homomorphic, has some homomorphic property that suffices for the server to, given the database and an encryption of the index, create an encryption of this value. Okay, and because it's an encryption, the server processes from an encryption to an encryption and doesn't know how to decrypt under some computational assumptions. But the ciphertext that the server eventually sends back can be decrypted by the client. So the client encrypts under their keys. The second flavor of solution is an information theoretic PIR without any computational assumptions. But the cost is that so it's rather it cannot be done for single server PIR, but once you have so you have n greater than 1 servers, each holding a copy of X. Okay, and the privacy. Focus. Privacy against some subset, less of T of servers, and usually is only one. Okay, so most of the solutions, target this this case. There is this whole thing gives rise to many variants of the question. We'll come back to them later, but one maybe that immediately jumps out is that what if X is private too from the servers? So what the servers hold is not copy of X, but shares of X. And could you support private information retrieval efficiently in such with such added constraint? All right, that the servers are not owners of X; there are outsourced servers, and you secret share X among them. And now you want to allow this set of trustees to service retrieval queries in a private way, and not only not learn about the indexes that are being retrieved, but have just shares of the database locally. Okay. So I will describe two solutions that are to both computational and private information retrieval that are basically the same solution in a disguise. Let's start with the for computational PIR, and the solution will use an ingredient additively, so additively homomorphic encryption, public key encryption. Although actually we don't need this encryption to be public key, but basically I think that every homomorphic encryption we know is already a public key type. So again, what's a additively homomorphic encryption? So encryption of two messages. There is some target group. So encryption maps the plaintext is a group, and the ciphertext space is also a group where there is some group operation, such that if we we will denote it as a multiplication. We take two ciphertexts, and what we get is an addition, is an encryption of the sum of the plaintext. Okay, and what this implies, which we'll use in a second, is that, well, if I take a ciphertext and exponentiate it to any integer, which stands for repeated multiplications x times. So therefore, this is the same. What I get here is that integer multiplicity of that integer with times n, right? And also if I have a bunch of ciphertexts and exponentiate them to some coefficients and multiply the results, what that corresponds to, right, by extension, is this will be a sum of the MIs multiplied by these Xi's coefficients. So this is a summation of Xi's MIs, of Xi MI products. Now, so here is an application that will help, intuitively might help in private information retrieval. If I give you a vector of ciphertext which are formed as encryptions of zeros everywhere except of one place, and zero again, and the one place will be the index. So MI, let's say, okay, yeah, sorry. So let me call, sort of do summation here over the j is the variable, and at some point I'm going to make the message equal 1. So and all these messages, mj is equal to 0 for all j not equal to I, right? So if that is my vector of ciphertext that I create, then if you take this vector and you then the product of cj's to xj's is an encryption of the sum of xj's mj's, right? So we knew that, but that is because all the mj's are 0 except of 1. So all the xj's except of the xi drop out because they are multiplied by zeros. And the only xj that is not multiplied by a 0 is the one for j equal 1, j equal I. So this is just an encryption of xi, okay? Because all mj's are 0 except mi. So this already basically tells you, like, look, I can do privacy preserving retrieval. I send a vector of ciphertext. The server takes his entries in matrix in vector X, and he takes my ciphertext, and this is what he does with these. He computes a single ciphertext, which by additive homomorphism properties will actually encrypt the ith element in the database. And by the secrecy of the encryption, he does not know which of these entries are zeros and which is the only non-zero one, right? So he learned nothing. So this is immediate, basically 1 out of, in fact, this is a 1 out n OT. We already knew this. This is precisely how we implemented OT. It's one of the ways, but yeah, that was the main one. I mean, the first one. So it's a 1 out of n OT, but does this solve the PIR problem? Not quite yet, because this vector of ciphertext that the client would have to send is linear in n, right? So it's the bandwidth is not sublinear. But here is a trick that maybe you see coming. Let's view x as a square root by square root array instead of a vector, n long vector. And let's do the above over rows of x. So think that somehow you can generalize this, and the x's here are not elements of the array, but whole rows. Okay, so at first it might not be so obvious, like how you do this exactly, but just somehow abstractly think that this encryption can be, with just a squinting your eyes, is going to implement that. So what the client knows his index that he wants to retrieve, right? The index, which is the index in the array. But once the array becomes a square root by square root matrix, well, he can translate this index into a column and row in the matrix where that position lies, right? So let this ciphertext be one in the, get it correctly, in the column which he wants to retrieve. So, and this is a multiplication by the whole row. Okay, no, so yes. So, no, sorry. So this has to be an encryption of the row that he wants to retrieve. And what would you get as a result, right? You would have the ith row. Because if these xi's are rows, and the index here is the only plain text that is not 0, is the one at position of the ith row that the client wants to retrieve, then what he gets is the ith encryption of the ith row. And now he can, well, it's not a metric PIR. He doesn't learn just the single entry, he learns the whole row in the square, so he learns square root of n entries. And what did we gain? Well, the ciphertext now is of length square root of n, because the positions here correspond to rows in the square root of n matrix, and the only one is the row that the client wants to retrieve. This ciphertext is no longer a single ciphertext. If this can be done for rows, basically this will be the size of the row. So the result is the size of the row. But that's square root of n. So this basically balances out, whereas this basic application of the homomorphic encryption had a n-sized client ciphertext and a constant size response of the server. in this full solution, the client's size ciphertext will be square root of n, and the server's response will be square root of n. But that's fine, right? We get 2 square roots of n, hence linear square root of n. So let's see how. So you got square root of n ciphertext c hat and square root of n response of the server. Okay, so let's see how to that this intuition carries through, right? That you can take this homomorphic encryption and basically do it over rows. So okay, so here is the two-dimensional view with square root by square root of n, and we will take. Here is my indexing. I will be the row, the column, and J will be the row. This is maybe not the best choice, but that's the choice I made. Here is the position, the IJ positions that the client wants to retrieve. So the client has IJ in this space square root of n by square root of n that identifies the place in the position in the array of x. So now x is the square root of n by square root of n array, and this is the position in the array that the client will retrieve. Okay. So the client sends to the server a vector of ciphertext, which is a vector of ciphertext c1 to c square root of n, which encrypts in some way something I will call an indicator vector at position I. So first, what is the indicator vector? So EI is a vector that is made of all zeros and a single one, and the single one is at ith position. Okay, and this vector is in is of dimension square root of n, right? So there is square root of n here. He encodes basically EI is a vector made of all zeros and a single one here, okay? And it will be a vector that will be applied to all the rows of X, thus choosing, hold on. So I will take every row and I will, hold on, am I doing it over rows or am I doing this over columns? So can I manage to confuse myself? Doesn't seem right. If I'm doing it over rows, then well, okay, yeah, yes, it's
I feel the problem is only on the drawing, because usually you think of the first coordinate of a matrix as the rows, and it seems you are using it for columns.
yes, right, but okay, yes, so right, when I look at it as a matrix, but you know, if this is an x-axis and this is a y-axis and this is an xy, so okay, let's go with this, and let's okay, and now here is my notation for so here are the rows of x. Okay, what does so this is the EI, and what is this E hat notation? It is a vector of ciphertext where the first ciphertext is the encryption, is the additive encryption, the underlying encryption of the first element in this indicator vector, right? And all of these are just elements in encryptions of elements in the indicator vector. So what's the property of the ciphertext? CJ is either an encryption of 0 if J is so let's call it I prime. If I prime is not I, or it's an encryption of 1 if I prime is I, right? So I'm doing what I was doing before, but over an indicator vector that that chooses a column. Yeah, that chooses a column in the in this matrix I want to retrieve. What does the server do with the stuff? Very similar as before. So the server computes its response as a vector of responses, which is a vector of ciphertext which I can represent, you know, in an abstract way as an as this vector encryption applied to a vector which comes from this application, this matrix multiplication. So if I take matrix X and multiply it by vector EI, then remember, vector EI is non-zero only at ith position. So what this application will do, it's basically it creates an xi, which is the ith column in the matrix X, right? Because all these rows are multiplied by this, and the only thing that is basically everything gets cancelled except of the elements in the ith column of X. And if so, this product is an ith column of X. If A is an encryption of the ith column of X, then so if that is true, then A hat A1 A square root of n encrypts the ith column of X. So just client decrypts the jth element of A to get this an entry at this position of matrix X. Okay, so let's see how the server can compute this this encryption, given the encryption of this ith indicator vector. I mean the indicator vector, right? That is one at the column I want to retrieve. Okay, so so how does S compute A hat, which is this matrix product? I mean the matrix vector product, given C hat, C vector, which is this encryption of the of this indicator vector. Okay, so okay, each element in A is so how do I compute this encryption? I take the jth row and this indicator vector, encrypted indicator vector, and I apply I basically multiply under encryption of X of the jth row with this encrypted and indicator vector. Okay, so this, what I want is to compute the jth row multiplied by the indicator vector, right, which I have under encryption. But using the homomorphic stuff, right, I can indeed, this is vector multiplication. So this is X multiplied by vector n, right? So that's exactly what I need here. So so this is a product of okay, so this is this this is a regular encryption. So it's a product of the regular encryptions of the jth element here, but to the hold on, I'm running out of these. Well, you know what? Let's not do this way. Let's do that way. So EIs where let's call them. Oh, okay, we already have. It's CIs. So it's a. So what's the first encryption here? It's called C1. And what's the first thing here that I want to take? It's XJ1, right? This is the XJ. So this is XJ1, XJ2, XJ square root of n. And here is how I will multiply them. Okay, which is by the encryption homomorphism is the encryption of xj1 times the first element of the indicator vector dot 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 xj square root the last element of the indicator vector, right? And all of this, because the indicator vectors are zero everywhere except of the ith position, so this will basically dig out the ith element into j's row. And that's AJ. So that's the element that, yeah. So this is created for each J. And the client will have, he can decrypt all the other AIs, these A elements, right? The first element here will encrypt this value. The second will encrypt this value, etc. So the client, if he wants, he can get the whole column, right? So as of now, this is not symmetric private yet. So C gets whole ith column this way, if he wants. Okay, and what was the bandwidth? And the bandwidth was, well, I had the ciphertext that is sent here was square root of ciphertext. Right, of this underlying additively homomorphic encryption, and the response likewise. What about, so it is sublinear. What about computation? Well, it's square root of ciphertext, basically encryptions and decryptions, right? So encryptions forming this, and decryptions, well, actually, he does only one decryption for this client. But what about the server? Well, the server needed to compute this expression for every row, right? So now these are just bits. So these exponentiations are, it's really one big mult where without loss of generality, I mean, okay, so in the worst case, you do square root of n mults. For every row, you have square root of n, so it's on mults. Okay, in the ciphertext group. let's postpone how to make it symmetric, and first talk about the information theoretic version of this. So far so good.
Yeah.
Okay. So the information theoretic version of this is really it's kind of the same idea, but rather than homomorphism of encryption, we'll use we'll basically compute on the plain text. We'll just use we'll use linearity of the fact that all of this was basically phrased in terms of linear algebra. The client chooses an indicator vector, and what he wants to get out is the result of the array, the database array, the array representing the server's database multiplied by this indicator vector. This can be done over plain text if in the two server setting. Okay, so take two server setting, and we continue with the two-dimensional representation of the array. So there is an ij location which the client wants to retrieve, and he forms the same ij indicator vector at ith position. And now there's two servers, S1 and S2, both of them holding this X that is now a matrix. Okay, and what the server does is that he secret shares this vector. So secret share EI to form two vectors, call them Q1 and Q2, such that Q1 is random in we need to think of this as a field. So it's a Z2, it's a binary field to dimension square root n. And Q2 satisfies the constraint that Q1 plus Q2 is EI, and this is over Z2, right? So this is a vector, this is a vector, they sum up to this vector. This one is chosen at random, and this is a difference between this and that, right? And what the client does is that he sends this secret shared indicator vector to the two servers. And client wants the jth the ith column of X, which is a product of X and this EI indicator vector, right? But by linearity, this is the same as X to Q1 plus Q2. So these two vectors secret share this one, where all the operations are over Z2. And but by linear algebra, this can be represented as this sum. So clearly each of these guys, the S1 can compute this part, S2 can compute this part. So that's what they do. The response of server 1 is this matrix multiplied by the first share of the indicator vector, and the response of the S2 is the same matrix multiplied by the second share of the indicator vector. All right, and so therefore this can be recovered if I just add these two responses, right? And so he gets what he wanted, and then so this follows that A, which is A1 plus A2, equals xi. So jth element of A is x at ijth position, right? It is the same exact arithmetics, right? But rather than have a homomorphic encryption that allow me to encrypt the indicator vector, and for the single server to compute the encryption of the ith row by using this homomorphic operations here, right? The servers now compute over the plain text space, but because they compute over the share of the indicator vector, well, they don't learn what EI is, right? Because the only information they get are these shares. So privacy is by secret sharing. Right? It is this is Z2. So this operation, the plus over Z2, is really an XOR, right? So this is simply an XOR sharing of this vector. And correctness we already argued. What about the cost? So the bandwidth, well, all of these things, so both the queries and the responses, are square root of n vectors over of bits, right? And what about computation? So, well, the client really does not do much computation, right? What the servers do is a matrix multiplication, but it's a matrix multiplication over Z2, right? So these are bits. The product is just a bunch of XORs, right? Well, the product is using these bits to select these and then XOR the ones that are selected, right? So it's order of n XORs. If you compare the cost of the two solutions, the computational and the information theoretic, right? You got square root for communication in both cases, and you got linear for the server. It seems that information theoretic didn't give you much, right? So at least asymptotically, getting these extra servers didn't get you mad. Well, what it did get you is well, it's really apples and oranges type of privacy. Here, the privacy was in the information theoretic solution, the privacy is conditional on these two servers not to collaborate, right? So each of them individually just gets a share, so that's perfectly hiding of this vector. But of course, if they get together, they reconstruct the secret sharing and they get the indicator vector, right? Conversely, this guy, there is nothing he can, he gets this encryption, there is no more, collusion possible, but it's subject to the computational assumption, whereas this one is not. Okay, so kind of apples and oranges there, but in terms of asymptotics, they are the same, but not. But you can see that in real cost, this one will win, right? Because, well, already in bandwidth, this is the square root of ciphertext. These are group elements, whereas these are just bits. So it's a security parameter gain, right? And of a factor of 100 or so, right, in the very least. And molds in a group versus XORs is, it's a huge jump in terms of concrete efficiency, right? I mean, there is no faster operation than an XOR, and whereas these are okay, not so trivial, right? So this is a public key type of operation, and if n is large, then this cost will start dominating. Okay. Okay, so these are sort of basic solutions to the problem. They are maybe what else is known about them. So so computational PIR, well, so this basic solution, right, which we have seen, is the bandwidth is square root of n, and this is Koszylewicz-Ostrowski already 20 plus years ago. This can be driven down to n to any constant, and all you need is homomorphic encryption as in here. So you can ask. So here is, we started from this. Hold on. Okay, well, it doesn't matter. There was a solution we gave prior to this, okay, which is the very simple usage of additively homomorphic encryption, where you send a whole vector, the encryption of the indicator vector, where you take the whole n as the space, right? Now, using the two-dimensional trick, we reuse this basic solution idea and drive the cost down to square root. You can the way to get here is by recursion. So it's not immediately obvious, but you can if you see how to recurse, you will get down here. This is incredibly high level statement. There's other type of solution flavors which okay, they're not greatly philosophically different, but they drove the cost down to polylogarithmic in but what they did is that they used stronger arithmetic assumptions, and particular strain of solutions came from so-called die-hiding assumption. It is that certain subgroups in RSA type of group are hidden by an RSA encryption, and at the this additive encryption that we use here was primitive in a way that the ciphertexts were hiding just 0 or 1. I take a row, I don't take a row. If I have a more versatile, if you will, encryption scheme, homomorphic encryption scheme, where I can basically pack more information into a single ciphertext that would encode, well, maybe not the whole row in a single ciphertext, but information about some chunk of rows or columns. And the encryption has the property that I can homomorphically, this guy can take this ciphertext over whole chunks of information and pack them into a single ciphertext. That's the kind of what the search for such encryption scheme and instantiating them from RSA type of encryption is where this thing came from. And there were also the improvements later on, okay, in terms of these assumptions and the concrete efficiency in here. Look, of course, this is the case at the end of this road, right? You have fully homomorphic encryption, because if you can, if you have fully homomorphic encryption, then given an encryption of this I, there is some process here that can take an encryption of a single index and apply some homomorphic properties to basically process this circuit that implements a selection, implements a lookup table. But fully homomorphic encryption is, significantly more expensive, right? If we, the cost of this basic one has a suboptimal bandwidth, right, driven down by usage of a more complex encryption, and is going to be driven to a constant times security parameter, right? But constant, so then using the most complex and homomorphic encryption, but the assumptions underlie will keep growing still, and the concrete efficiency for the server computation, rather than this is still homomorphic encryption is El Gamal. You can do it in prime order groups, right? So the shortest elliptic curve would work, right? Here you have to go to RSA setting. The implementations of RSA operations are much longer, right, and much larger and costlier for the server, right? This stuff is costlier still. So it's a trade-off between bandwidth and concrete cost of server computation, which is linear in all cases, but the concrete costs changes. And then information theoretic PIR, okay, so this the basic stuff I told you, right, is this. And okay, so the citations, sorry, I don't have a big list, but you go to case servers, and actually I don't know whether this is the current, still the current best, but for a while this was the bound on bandwidth. And so, for example, for two servers, you can, this is 1/3. How do you get down from this basic solution, which is called root, to 1/3? And if it is recursion, then how come that the recursion somehow bottoms out, right? And does not give you the same well, and how to generalize it to more servers to drive the cost down even further, right? And this there is a better asymptotic cost later, but not sure about concrete efficiency. So some, some of the, and the asymptotics is not dramatically better than this. There is also a lot of work on lower bounds for this because of these gaps. And the lower bounds, there is work on them, but they're not matching, and or they only work for some restricted setting, like, for example, a single round, which actually this protocol is, right? But I don't know whether these are single rounds. Forget that. And there are some other restrictions in these lower bounds. Maybe the last things I want to mention quickly is the extensions. So one is symmetric PIR, right? How to go? But basically, there is symmetric PIR. You can go by generic compilers to symmetric PIR. For example, you can use oblivious to the random function that we mentioned last time. So if the well, okay, so this compiler does not look very general, but it can be put in a general form. But if all of these solutions, the two solutions, which were in a sense the same solution, just cast in two different settings, the server's response is some vector like this, where C should only learn the jth one. So, right. So how about this? S can encrypt the jth element in the vector by a PRF where K is S's key. Okay, so he is in a counter mode. He creates these values and he encrypts this with that used as a key. And then CNS engage in OPRF like this. The server has a key, the client has this one value that he's supposed to learn from these, right? They run OPRF. This guy does not learn which value that was, but this guy learns FK of J. So he gets the key to decrypt exactly the jth element here, but no other, right? And so this fit, it can be generalized to basically compile any solution as well. Another, so there is many usage of PIR, and but here's a maybe very natural question: how to extend PIR so that rather than the client has an I and the PIR allows the client to recover I's position in array S, right? Keyword PIR would X is a set of keyword value pairs, right? The client has a keyword and a keyword pair, keyword PIR, right, allows the client to get V such that KV is in the set, right? So a value associated with this keyword in the server's database. Can you do a general compiler that takes a symmetric PIR and creates a keyword PIR? Or perhaps you take these solutions, which so far it's really one solution, and try to extend them, force them to be in this regime, to work in this regime to begin with. And another question is, can you combining computational and IT PIR result in efficiency improvements? So there's two solution classes. You have many servers and you get information theoretical privacy, or you have a single server and you get a computational privacy. Okay, let's say in practice you don't care about information theoretic secrecy. You are allowed, you work under some assumptions. Is the fact that you have two, if you have two servers rather than one, could you get faster computational PIR in a way? Okay, or looked another way, could you get bandwidth improvement for information theoretic PIR? So, could you drive down these costs to something like this, but perhaps not use such strenuous assumptions, and the concrete efficiency would be closer to this stuff. Okay, and one result like this is from comes from distributed point functions, and that's what I wanted to talk about next lecture. Okay. Any questions?
No, it was very understandable.
Okay. All right. Okay. So see you next time.
Okay, see you. Bye.